Hi, Ms. Heaton signing in to talk about our last topic in equilibrium. Today we're going to be looking at how KEQ can apply to a special case related to solubility. So we're going to have to think back to Unit 7 a little bit as we talk about how equilibrium applies to those situations. As you may or may not have guessed, KEQ applies in a wide variety of situations for anything that can get to equilibrium, and this includes dissolving or solubility. So just to remind you of what we learned at the beginning of the semester, solubility basically means that when a solid is added to a solvent, it starts to dissolve. For example, if we had calcium fluoride, CaF2, it might look something like this. And if it was a solid, it would be together in a compound, a formula unit. And when it dissolves, it would break up into calcium ions and into two fluorine ions, each with a negative charge. So that's what dissolving means. Now, there is a point at which no more can dissolve, and that is the saturation point, and we're going to be dealing with that today. But in any situation where you have something dissolving, it is actually at equilibrium. We didn't talk about that when we learned about solubility, but it actually does apply. Eventually, the amount of calcium fluoride that is turning into calcium and fluorine ions will equal the amount of calcium fluoride ions that are recombining to make calcium fluoride. Remember, equilibrium doesn't mean equal amounts. It means that you have the forward and reverse reactions happening at equal rates. Now, let's talk about how this applies to solubility. Another word for solubility is the measured solubility, the amount that we measure that can dissolve. It's the maximum amount of moles of that solute that can dissolve per liter of solution. So basically, if I tell you the measured solubility of calcium fluoride at 10 degrees Celsius is 10 grams, that means that 10 grams, I guess I probably wouldn't use grams units anymore. We're going to use molarity now that we know what that is. What if it was 10 molar? That means that 10 moles of calcium fluoride would be able to dissolve in 1 liter of solution at its saturation point or at its measured solubility. So if I tell you this, we're going to talk about how this applies to KEQ in a minute, but it's important to notice that the solid's concentration will be 0 at equilibrium. If you start out with an amount equal to its measured solubility, so if I started out with 10 molar of solid calcium fluoride and its measured solubility was 10 molar, at the end I would have 0 molarity of it left. Well, duh, right? Okay, well let's see how this applies to equilibrium constant calculations. Today, instead of using KEQ, we're going to use the variable KSP, which is just a special kind of KEQ, but it deals with solubility product constants. So we're going to be dealing with something dissolving and reaching its maximum solubility. For example, let's take that calcium fluoride example. We would write a KSP equation just in the same way that we would write a KEQ equation. So if you had calcium fluoride, it would dissociate into calcium ions and into two fluoride ions. And you notice that the calcium fluoride is solid, so it will not appear in our KSP equation. In KSP, you will never have a reactant side. The denominator will always be just a solid, so it won't appear. You will only have your products. Hey, I wonder if that's where they got the product part from. And this would be fluorine to the second power, and they'll be multiplied by each other. So that would be our K expression, our KSP for calcium fluoride. And like I just said, remember, solids will never be included in any K expression, including KSPs. Here's the kind of question that I might ask you to solve related to solubility product constants. We'd like to calculate the equilibrium concentration, so the E row in our ice chart, for ions of the dissociation of silver 1 carbonate. Uh-oh, we're going to have to know how to name. Yep. Okay, and we're given its KSP value as this. So the first step is to write the reaction that's occurring. If it's silver 1, that means silver has a +1 charge, and carbonate is CO3 2 minus. You remember that, right? If not, better go review it. So carbonate has a -2 charge, so we'll crisscross the charges and have Ag2CO3. That is our solid that we are starting out with. And we're going to dissolve it into its ions. So that will break into an Ag, actually 2 Ag plus 1s, and 1 CO3 2 minus. So that would be our reaction. You know, people often find that that is the hardest part of doing these calculations. We'll make an ice chart, and we'll write our K equation. KSP will be our two products multiplied by each other. And remember, solids don't count, so that won't show up in our KSP. So now let's fill in our ice chart. We actually don't know any numbers that go there, although we know that we're only starting with solid, so we'll have 0 of our products to begin with. And we know that the change row would be minus x for our reactants, and plus 2x, because there's a coefficient of 2, and plus x for the carbonate. And then in our equilibrium row, we'd have x for CO3, 2x for Ag+. We don't know what concentration of silver 1 carbonate we started with, but does it matter? Actually, it does not, because remember, solids aren't going to show up in our KSP equation, so we can ignore that first column for the solid. Now this is just like the quadratic or the square root or the approximation method, where we take our equilibrium row and plug it into our KSP equation so that we can solve for what x is. So the KSP value we were told is 8.1 times 10 to the negative 12th. That's going to equal Ag's concentration at equilibrium, which is 2x squared, and CO3's, which is just x to the first. So if we combine those terms, that'll be 4x to the third. You will, if you do enough of these, you'll start to notice some patterns in terms of what will be on this side in your KSP when you plug in x. And then, folks, from there, it's just kind of an algebra calculation. Divide both sides by 4. You get x cubed equals 2.03 times 10 to the negative 12th. And then cube root both sides. So x will end up being 1.27 times 10 to the negative 4th molarity. Then remember, we're looking for equilibrium concentration. So once we found x, we just plug that back in to our E row. So 2 times that number will be the concentration of Ag+. So that ends up being 2.5 times 10 to the negative 4th molarity of Ag plus 1. And it would just be 1.3-ish times 10 to the negative 4th molarity of the carbonate. Not too bad, right? No square root or approximation or quadratic even needed. Okay, we have one more kind of problem that I could ask you to do, and that would be like this. Copper 1 bromide has a measured solubility, ooh, that term should ring a bell from earlier in your notes, of 2 times 10 to the negative 4th moles per liter, or molarity. Calculate its KSP value. So this is like the problems where we had to find the value of KEQ, still using an ice chart. So again, we're going to start the same way. The hardest part seems to be writing the formula for copper 1 bromide. Copper is plus 1 because of the 1. Bromide is minus 1 from the periodic table. So it's plus 1 and minus 1. Those cancel out. So that's our solid. And it's in equilibrium with the ions it'll break into, which are copper plus 1 and bromine minus 1. So we'll make our ice chart. And we'll write our KSP equation. KSP will be copper plus 1 times bromine minus 1. And both to the first because they have coefficients of 1 and 1. For our I row, okay, initially we start out with 0 of our products. Let's switch to black. 0 of our products. And of our reactants, we'll have this measured solubility. Let's refer back to above here for a minute. Remember, measured solubility is the maximum number of moles that can dissolve per liter of solution. So for these problems, what we'll do is assume that we're starting with the maximum amount that can dissolve. That way, we know that all of it will dissolve. So when we do our change row, we know that at the end we'll end up with 0. Our change row here will be plus x and plus x because the coefficients are 1 and 1. So this will be x and x. Okay, so this is the unique step. You take the measured solubility, you put it in the I row, and at the end you have 0. Does that enable you to solve for anything? Why, yes, it does. That means 2 times 10 to the negative 4th minus x equals 0. So x has to be 2 times 10 to the negative 4th. So you can plug that in for x, and then plug those in to your KSP equation over here. So KSP will be the product of 2 times 10 to the negative 4th times 2 times 10 to the negative 4th, which turns out to be 4 times 10 to the negative 8th. No units because it's K. And folks, that is solubility product constant calculations. Hard to say, not too bad to do. Come to class, we will practice a little bit more. Ms. Heaton signing out.